So for the do now, this is actually reviewing some things from acid-base from the prior chapter. So number 1 is looking at the conjugate base for acetic acid, and number 2 is actually calculating the pH of strontium hydroxide. So for number 1, write the conjugate base for acetic acid. So first, we need to know the formula for acetic acid. So remember when you're naming acids, if it's a polyatomic ion, so acetic acid is coming from a polyatomic ion. If it ends in ic, that means it had the ate ending. So we're looking for acetate within the acid. So if it's an acid, it starts with a hydrogen. And then we have to think about the acetate polyatomic ion. And you could write it 2 different ways. I'm going to write it in a simplified way. So acetate is C2H3O2. Carries a -1 charge. Well, hydrogen would carry the +1 charge. So the formula for acetic acid is just HC2H3O2. So then we're looking for the conjugate base. So remember, the conjugate base is after the acid loses in H+, because it donates in H+. So once it donates in H+, it becomes the conjugate base. So we're just going to remove this hydrogen that we put at the beginning. We're going to remove that H+ at the beginning. You're removing an H and a +1. So it's going from a neutral charge to -1. So the acetate ion, C2H3O2 minus, is the conjugate base. This is our answer for number 1. The conjugate base always has 1 less H+ than the acid. Then number 2, strontium hydroxide has a concentration of 0.50 molar. What is the pH? As we start getting into more and more of these problems, especially today when we're looking at common ion, you need to label all of your substances. Label whether it's a strong acid, a weak acid, a strong base, a weak base. Label all of those. So hydroxide, if it ends in hydroxide, it tells me it's a base. If you remember the strong bases on the periodic table, make that lowercase b. So lithium all the way down, calcium down. Makes that lowercase b. Strontium is part of that lowercase b, which means that strontium hydroxide is a strong base. And what that means is if we have strontium hydroxide, so it's SR2 plus and OH minus, so strontium hydroxide is SrOH2. Because it's a strong base, it's a strong electrolyte, it completely dissociates into SR2 plus and 2OH minus. So this is important as we're looking at anything with acids and bases, or as we're looking at common ion today. It's important that we can label acids, bases, salts, because anything that is a strong electrolyte, so that's a strong acid, a strong base, or a soluble salt, it will break apart completely. So this says that we have 0.50 molar of strontium hydroxide, and it's asking us to find the pH. Well, based on what I see here, I might be able to do something with the OH minus. So what I'm going to do is I'm going to figure out how much OH minus do I have, and then I can manipulate from there. So here's where this equation is really important, because if I have 0.5 molar strontium hydroxide, notice how we have twice as much OH minus. So if we think about it in terms of stoic, for every 1 strontium hydroxide, we have 2 OH minus. 0.5 times 2 is 1 molar. So we have 1 molar. I don't actually need this right now. We have 1 molar hydroxide. Now, I know if I need pH, I'm probably going to be using logs. If I take the negative log of 1.0, this is OH minus. If I take the negative log of OH minus, what am I actually finding? Is this pH?
That's
POH. Right, if you take the negative log of OH minus, you're actually finding POH. So if in your calculator you do negative log of 1.0, right, and I'll do it in mine just so that you know I'm not lying to you. Negative log of 1 is 0. Negative log of 1 is 0. You can have a POH or a pH of 0. That's okay. The scale is from 0 to 14. So if the POH is 0, what's the pH? 14. Because remember that pH plus POH equals 14. And it makes sense that this is all the way at the top of the pH scale because strontium hydroxide is a strong base. So we have a high concentration of a strong base, the pH is going to be high. So this is just reviewing things that we've looked at with conjugate acids and bases, and then strong bases and looking at pH. Because we're going to be using this, we're going to be using a lot of the stuff that we were doing in the last chapter in this chapter as well. Any questions on the do now before we go to the common ion examples? So then what we're going to do is we're going to just jump right into the common ion examples. So in the notes, we're going to be on page 16. So in the notes, we're going to be on page 16. So all of the examples are at the end of the notes packet. Here we go. So example 1. Yesterday we talked about the common ion effect. We did the demonstration. If you need to go back and review that demonstration, I did record it. I posted it on YouTube. And so you could go back and review that if needed. For this example, it's asking, does the pH increase, decrease, or stay the same on addition of each of the following? So let's think about what this means when it's asking about pH. So does the pH increase? So if I think about what that means, if the pH is going up, it's becoming more basic. Right, more basic actually means less H+. More basic, more OH minus, less H+. Does the pH decrease? So if the pH is going down, it's becoming more acidic, which means more H+, or stay the same. Right, so there'd be no effect. So we're looking at how pH will change. Is it becoming more basic, more acidic, or is nothing happening? And we have 5 different scenarios. So these are common ion problems. Now some things that we want to think about, we want to keep in mind with common ion problems, and I'll write it over here. The first thing that we want to do is to identify every substance. And when I say identify every substance, you want to think about, is it a strong acid? Is it a strong base? Weak acid, weak base, or is it a salt? Because remember that strong acids, strong bases, and soluble salts, which usually will be potassium, they'll have nitrate, they'll have ammonium or sodium or chloride for dealing with weak bases. Those are always completely soluble. They completely break apart. Weak acids and weak bases exist at equilibrium. The second thing that we want to do is write the equilibrium equation. Of the weak electrolyte. So weak electrolyte means either weak acid or weak base. Because in order for the pH to change, or in order for there to be any kind of change, when we add a common ion, it needs to be at equilibrium. If it's not at equilibrium, there's no shift. There's no Le Chatelier's principle happening, or there's no Q versus K happening. We always need a strong electrolyte, so a strong acid, strong base, or a salt. We always need a strong electrolyte in order for there to be a common ion problem, because we're looking for what they have in common. So if we start with part A, I'm going to start just by identifying the substances. NaNO2. Well, I notice I have sodium nitrite. It's not an acid, it's not a base. This is a salt. It's a salt because we have sodium with a polyatomic ion. So NaNO2 is a salt. We're adding that to a solution of HNO2. So here's where you need to think back to your 7 strong acids. I know it's an acid because it starts with an H. So I know it's some sort of acid. NO2. That's nitrous acid. That is not one of the 7 strong acids, so that's weak. So I have a salt, which is a strong electrolyte. This will break apart completely because of the sodium. And I have a weak electrolyte. I have a weak acid. So what I want to do is I want to write the equilibrium of whatever is weak. Weak acids and weak bases exist at equilibrium. So HNO2 exists at equilibrium with H plus and NO2 minus. So here's my weak acid. Now, the reason that we have a salt is because notice here's our common ion. You need a strong electrolyte in order for there to be a common ion, because if I put this NaNO2 into this solution, there's water in here, we're just not showing the water. I put this into this solution with water, this is going to break apart into ions. Because it's a soluble salt, it has Na plus in it, it's going to allow it to break apart. So this actually has NO2 minus. So if I put NaNO2 into this solution, I'm increasing the amount of NO2 minus. So now it becomes like a Le Chatelier's principle question. So this was before I added this NaNO2. This is at equilibrium. Now I add more NO2 minus. So now I have too many products. I have too many products compared to reactants. So this reaction has to shift to use up what was just added to get back to equilibrium. So to get back to equilibrium, we need to use up this NO2 minus. So to use up the NO2 minus, the reaction will shift to the left. So the reaction shifts left, or we could say the reverse reaction proceeds. So as the reaction shifts left, I'm using up the NO2 minus that I added, but I'm also using up the H plus. Because as the reverse reaction proceeds, H plus and NO2 minus are combining to form HNO2. So from adding this common ion, the reaction shifts toward the left using up H plus. So the question is asking what happens to pH. So we have less H plus. As the reaction shifts left, we have less H plus. Less H plus means it's becoming more basic. More basic means the pH increases. So this is thinking about how the reaction shifts, because remember, as we add a common ion, we are not changing the equilibrium constant. The only thing that changes the equilibrium constant is temperature. We are looking at Q versus K. We're looking at the reaction shifting to get back to equilibrium. So if we take a look at B, let me go back and forth on the screen. Part B, we have CH3NH3Cl. It's added to a solution of CH3NH2. So I'm going to skip this first part for now. I'm just going to come to this second part. We have NH2 at the end. Remember that NH2 group is called an amine, A-M-I-N-E. An amine is a weak base. An amine is a weak base. Now that we labeled the weak base, it might help us a little bit. Here I have Cl at the end. CH3NH3 looks similar to CH3NH2. This is actually the conjugate acid. This is a salt. I know it looks weird, but it's a salt. When we're dealing with weak bases and we're looking at a common ion, a lot of times we see a salt that ends with Cl to bring in that common ion. So let's write the equilibrium of this weak base. CH3NH2, because it's a base, I'm going to show water in the equilibrium. Remember, acids we can actually ignore, right? There is plus H2O here, and this is H3O plus. We just simplify it. Bases are a lot harder to simplify. CH3NH2 plus H2O, so this is a base. All right, if we think about what our products are, this, because it's a base, will accept a proton. And H2O will become OH minus. There's my equilibrium. We're writing the equilibrium of whatever the weak electrolyte is. In this case, it's a weak base. Now notice, take a look at that equilibrium. See how we have CH3NH3 plus? Well, if I remove this Cl minus, we have CH3NH3 plus. There's our common ion. So my common ion, I'm adding CH3NH3 plus to what we already have at equilibrium. This is like what we looked at yesterday with ammonia and adding NH4 plus. So we're adding CH3NH3 plus to what was already at equilibrium. So we're adding CH3NH3 plus. Every time we add a common ion, notice how it shifts the other way. So again, the reaction shifts left. The reaction shifts left because we need to use up this excess CH3NH3 that was added. But as it shifts left, we also are using up OH minus. So now we have to think about it a little bit differently because now we're thinking about it in terms of OH minus. So less OH minus. Think about it in terms of H plus. Remember, OH minus and H plus are inversely related because H plus times OH minus equals Kw. So less OH minus technically means more H plus. H plus tells you how acidic it is. OH minus tells you how basic it is. So more H plus means more acidic. So our pH decreases. You can also think about it like we did in the demo yesterday. Less OH minus means less basic. Less basic means more acidic. So the pH is going to go down. So every time we add a common ion, the reaction shifts back to the reactants. We actually are reducing the amount of ionization. We take a look at part C. Sodium formate to a solution of formic acid. Starts with sodium here. Unless it's sodium hydroxide, sodium is probably going to be a salt. So this is our salt, sodium formate, to a solution of formic acid. So here's our acid. That is not one of the 7 strong acids. So here's a weak acid. So start by writing the equilibrium. Start by writing the equilibrium of whatever is weak. So HCHO2 is an acid. So it's at equilibrium with its ions. So if we have just a beaker of formic acid, this is what is happening in the beaker. The weak acid is at equilibrium with H plus and CHO2 minus. Meaning that there's acid, but there's also H plus, and there's that conjugate base. Now, sodium formate. Right, formate is CHO2 minus. That's that conjugate base. So let's think about it. We add more formate. We're adding a common ion. We add a common ion, the reaction is going to shift in a way to use up that excess common ion. So reaction shifts left, as they have in all of them. As it shifts left, we're using up the excess formate, but we're also using up H plus. So this is going to be like part A. We're also using up H plus. So as the reaction shifts, we have less H plus, because the H plus is being used up to go back to the reactants. Less H plus means less acidic or more basic, so pH increases. So yes, the reaction shifts the same way every time you add a common ion. But notice how it's not just H plus. Sometimes we're looking at OH minus. Part D. So part D, I'm going to write up here, I don't need as much space. Let's label everything. Potassium bromide. So potassium bromide, K plus and Br minus, KBr, this is a salt. It's an ionic substance, metal and a nonmetal, to a solution of hydrobromic acid, that's HBr. So this is a salt, strong electrolyte. Because it has potassium, it breaks apart completely. Hydrobromic acid, that's one of the 7 strong acids. So if you take a look at what we just labeled, we have a strong electrolyte, which breaks apart completely. We have a strong acid, which breaks apart completely. Do we have anything in part D that exists at equilibrium? No. So there's going to be no change. Part D is going to have no change because there's nothing at equilibrium. There's no shifting happening. Because if you write the dissociation of HBr, it's H plus and Br minus. You can add as much Br minus as you want into that beaker, but because it's a single arrow, it's not at equilibrium, it's not going to shift. Yeah?
Wait, so KBr is ionic and then HBr is a strong acid and both are strong electrolytes?
Yes.
Okay.
Yeah, so they both break apart completely. And so since we don't have anything at equilibrium, there's no shifting when we add a common ion. Yep. So then part E is a little different. So I'm going to look at part E kind of right down in here, just so I have some space. So part E. HCl is added to a solution of NaC2H3O2. So HCl is a strong acid. HCl is one of the 7 strong acids. Added to a solution of NaC2H3O2. Now, you look at this right away, you're like, well, this is a salt. Yeah, it is. However, if we think back back to our salts, Na is always neutral. Na plus is always neutral. Na plus is also always a spectator ion. Notice how in all of these, sodium is typically what is used in the salt. So part E, because we have a solution of sodium acetate, acetate, C2H3O2 minus, is actually what we will have in the solution. Acetate, if you look at the do now, is a weak base because acetic acid is a weak acid. So since acetate is a weak base, I'm going to write the equilibrium of the acetate ion. It becomes HC2H3O2. And so we'll do this just really quick. So we're adding HCl. HCl is a strong acid. Now you might look at this right away and say, okay, well, I don't see a common ion here. And you're right. This isn't a true common ion problem. However, what we are adding to this solution is lots of H+. Right, we're adding lots of H+, because HCl is a strong acid. Well, if we're adding lots of H+, we're making the solution more acidic. So the pH, it's becoming more acidic, the pH is going to decrease. There's one more example, and then hopefully you'll have some time that you can start working through mastering. There are 4 common ion questions in mastering. So numbers 1 through 4 deal with common ion. Example 2, this is a math question. So this says using equilibrium constants from Appendix D. So you will still want to have Appendix D available, right? Have it handy. Now, on example 2, you have, I think, the Ka value already written in your notes for you. However, on mastering, they will not necessarily give you the Ka or the Kb values. You need to use Appendix D for that. So remember, on the front page of Appendix D, you have Ka. At the top of the back of Appendix D, you have Kb values. Kb values are for weak bases. So this says using equilibrium constants, calculate the pH. So my goal is to calculate the pH of the solution containing 0.060 molar KC3H5O2 and 0.085 molar HC3H5O2. So this is propionic acid. So propionic acid, and then this is potassium propionate. We need to label. The first thing we should do is identify which solutes are strong electrolytes, so strong acids, strong bases, and salts, and which are weak electrolytes, weak acids or weak bases. This has potassium at the beginning. This is a salt. Typically, we will see salts starting with potassium or sodium or ending with chloride or nitrate. So this is a salt because it starts with K+. So potassium, nitrate, ammonium, sodium, and sometimes chloride are always soluble. So this is a strong electrolyte, meaning that it will break apart completely into ions. Propionic acid is not one of the 7 strong acids, so that's a weak acid. The importance of identifying is to write the equilibrium of whatever is weak. So I believe in your notes you already have it written down. You have the equilibrium already written, H+, C3H5O2 minus. So you write the equilibrium of the weak electrolyte, the weak acid or the weak base. That helps us determine the common ion. So between these two substances, propionate is the common ion. The only difference between what we were doing before and what we're doing now with the common ion is that when we set up an ICE table for an equilibrium calculation, because weak acids and weak bases exist at equilibrium, the only difference is instead of only having the initial concentration of the acid, we also have an initial concentration of a common ion. So I have 0.085 molar of the acid initially, nothing regarding H+. However, I have 0.060 molar of the propionate ion initially. So the difference between what we were doing before is these were both 0. Now they're not both 0. With the common ion, we have an initial concentration of whatever the common ion is between the two. The reason that this is 0.060 is because when this is placed in this solution, remember it's plus water, because of the potassium, that makes it a strong electrolyte. It breaks apart completely. So in the beaker, you have K plus floating around, but that's neutral. That doesn't participate in anything. And then we also have this propionate ion floating around, so that's going to affect this equilibrium. So once we have our equilibrium equation, we set up our ICE table, we fill in our values, and then we can solve like we've done before. So I don't have anything else. This is what they gave me. So now I'm going to use x's. Now the reason that I know it's still minus x and plus x on the right is because H plus is starting at 0. It has to increase. So 0.085 minus x, x, 0.060 plus x. So we've plugged into our ICE table. And now our goal is to calculate pH. So I know I'm going to need H plus at equilibrium. So I need to solve for x. This is where Appendix D and the Ka values are going to be useful. Because Ka, the reason that it's Ka is because this is a weak acid. Produces H plus in solution. So Ka is the concentration of H plus times the concentration of the propionate ion over concentration of the acid. Now I know they gave you Ka in your notes, but if they didn't, you look on Appendix D, propionic acid. Ka is 1.3 times 10 to the negative fifth. Again, this came from Appendix D. And then we just plug in our values for x like we had done before. X times 0.060 plus x over 0.085 minus x. Now, if you start looking at this and you're like, that's going to get really complicated. Well, what did we do to make it easier and not have to use a quadratic? Assume x is small. Now, when we assume x is small, not only are we assuming that x doesn't affect 0.085, we're also assuming that x does not affect that 0.06 on the top. So we're assuming that x is so small that it's not going to affect either of these values. Because now we have 1x that we're solving for. So 1.3 e negative 5 times 0.085. Then I need to divide by 0.06. So again, I multiply 0.085 over. Then I still have x times 0.06, so I divide 0.06 over. for x, we get 1.84 times 10 to the negative fifth. 1.84 times 10 to the negative fifth. That's x. Now here's why we assume x is small. I want to show you with this equilibrium row. If I plug x back into this equilibrium row, and you do 0.085 minus 1.84 times 10 to the negative fifth, if I kept it to 2 sig figs like this, you still get 0.085. X is 1.84 times 10 to the negative fifth. But if I do 0.06 plus 1.84 times 10 to the negative fifth, I'm still getting 0.06. So see how x is so small that it doesn't actually affect these equilibrium concentrations. Now calculate the pH. So if I take the negative log of 1.84 times 10 to the negative fifth, this is H+. So I am calculating pH here. So negative log of 1.84 be negative 5, 4.74. You have 4.735. So you can round to 4.74. So the pH of this weak acid, when we add a common ion, is 4.74. Now just a note down here, you could also be asked to calculate percent ionization. So you could be finding percent ionization of just the weak acid. So remember, percent ionization is the concentration of H+ at equilibrium over the initial concentration of the acid times 100. There's a question in mastering that has you calculate the percent ionization of just the weak acid. So before you add anything, so this is a 0 again, figure out H+ at equilibrium, calculate percent ionization. And then it has you calculate the percent ionization with a common ion. So you do the same thing. What we're getting into now is you just have to pay attention on if you have a common ion. If it's just a weak acid, then we calculate it just like we did before. Concentration of the acid, 0, 0. Do calculations. If there's a common ion, then you're going to have more than just one initial concentration. You could have a common ion that is a strong acid, so it gives you H+ initially. And you could solve that way. There is a video on the practice playlist where I go through additional examples for the common ion. So 3 or 4 extra examples. So if you want to go through, looks at some of the examples, they're not in the notes, they're just extra common ion. Any questions on example 2? It's the same as we've been doing. Using ice tables, you just have another initial concentration. So I'm going to skip this one. And so for the rest of class, if you want to take a look at mastering, all right, there's 4 questions on mastering. We have 12 minutes. So if you want to look even at a couple on mastering, common ion questions are just 1 through 4. So just numbers 1 through 4 is the common ion effect. And then for tomorrow, you'll watch video 8.2. I don't know how far we'll get into buffers tomorrow, but I just want to make sure you have that video watched for tomorrow. The notes for 8.2 starts on page 4 of the notes packet. Pages 2 and 3 are something that we're going to do together in class. We didn't have time to get to it today. So just know that the notes for 8.2 starts on page 4 of the notes packet. But just watch that for tomorrow. It's already up in classroom. So you can use this time to work on mastering. If you want to work together, ask questions on it, grab a marker. You can work on the desks.